We okay?
Yeah.
Yeah. Okay, let's make a start. So today we're going to be talking about what's called language modeling. And language modeling can be best described as how do we model a language? How do we know whether a sentence in the language is good in the language? And I don't say in the language, it's okay in the language or not okay. I really would like a score because I'm going to do comparisons between a whole bunch of marginal things. And so I would like to know that this is a pen is a good example of English, while pen this is not. Okay? Now, we all know that, but I'd like to actually have some mathematical function that I can use that will give me a score to tell me which one is better. Okay? This is a fundamental part of natural language processing. We're doing any notion of generation whatsoever, or any notion of choosing between things. What we really would like is a score of, and it's not really grammaticality, it's something to do with expectedness of the sentence. Is there something better or worse about it? So look at the next one, okay? And what I'd like you to do, okay, for the two of you who don't speak Chinese, okay, I'd like all of you to do this, is to read the 4 sentences, okay, which are there. If you do speak Chinese, you can see that they're translations of the Chinese, okay, but there are 4 sentences there. None of them are grammatically wrong, but some of them are better than others. And I'd like you to read through and decide which one you think is the most likely example of English, the best example. Okay, so I'll take a little time to read through. I can't remember which one I think it is. Okay, so who thinks, I'm going to number them 1, 2, 3, 4, just the English ones, the last 4. I'm going to number 1, 2, 3, 4. Who thinks number 1 is the best? Number 2 is the best. You're running out of options. Number 3 is the best. And number 4 is the best. Oh, so majority vote. We end up with number 4 is the best. Okay? Why? Yeah. Yeah. So things like the main content seems better than the chief contents, maybe. I mean, the chief contents is fine, but main is sort of slightly better.
There's no extra prepositions.
There's no extra prepositions, so we end up with things like he briefed 2 reporters. It doesn't sound quite native. It's not necessarily wrong, but he briefed reporters sounds better. Okay? And so there are these little subtle things that are going on, and if we took votes on sentences from all of you, we could get probabilistic, sorry, we wouldn't really be necessarily probabilistic, we could get some form of score from the group about which ones were good and which ones are bad. Okay? And that would be really useful to get that function, although it probably isn't a good function to, we just keep putting sentences up on the board and you have to vote and not vote, and then we give values back and we all turn into random Amazon Turk workers and do this for 1 billion times for Google. Not a good idea. They'll get paid better by Google than just identify percent. So we want a computer function, okay, that can look at a string of words and tell us and give us a score that's going to be appropriately relative in value depending on how good the sentence is. Now, that's a little interesting about what we mean by good, okay? Because I haven't really defined what good is. Good is more people vote that it's better. Well, that necessarily doesn't mean good, okay? I've said something about grammaticality, I've said something about probably word frequency, maybe, that might have something to do with it. Unusual sequences, something. And so let's actually go a little bit closer into that. So, for much of this lecture, we're going to care about probabilities, okay? You are expected in this class to already have done some piece of math work where you know what probabilities are, okay? And I know you were all desperately awake and excited in these classes, okay? So I'm just going to remind you some things, okay? So, and I'll be using this notation. So random variables take different values depending on chance. So if I talk about a random variable x, okay, what I mean is every time I look at that variable, it's going to have a different random value in some domain, okay? We're going to talk about the probability of capital X equals x, so that's the probability that the random variable capital X equals some particular value. So imagine x is a word in the English language, okay? And lowercase x, a particular word. So what's the probability of capital X is the word chair? Okay, so what's the probability of that? I don't really expect you to know that number, okay? But what happens if I say the probability of X equals Nebuchadnezzar? Nebuchadnezzar was the king of Babylon some time ago, okay? Now, what's the probability that a random word in English is Nebuchadnezzar? Okay, you again probably don't know. However, do you think the probability of a random word in English being chair is greater or less than a random word in English being Nebuchadnezzar? Greater, okay? It is more likely during your day here at CMU, you will hear the word chair than hear the word Nebuchadnezzar. Okay? However, you did come to this lecture and maybe you're going to sleep immediately afterwards, and I've already said Nebuchadnezzar 3 times and I've only said chair 2 times. Okay? So chair, chair, chair. Okay? Just to make sure that I'm not making things up. Okay? Yeah. But in general, chair is a much more frequent word than the word Nebuchadnezzar. That's still 1-1. That's still chair. Okay. Probability of small x is based on the probability of Nebuchadnezzar, probability of chair, and capital X is probability is a distribution function over all of the words. We can talk about the joint probability, we can talk about the conditional probability. We talk about the joint probability of what's the probability of x, capital X is x, or probability of capital Y. Or we can also say, given that the probability of something is y, what's the probability of x? And that's different, okay? If I said we were looking at sequence of words, and I said, what's the probability of the word Trump and the probability of the word president, okay? You could give me probabilities, but I would said, if I gave you the word president, what's the probability of the word Trump? It's going to be more if you just take them as isolated forms, but if I said president and introduced it into the conversation, you're more likely to hear the word Trump. Let's try the simplest of models, called the unigram model, unigram meaning 1, and gram meaning written form. And what we can actually use, we try to model the English language by looking at the probability of each word, okay, in a sentence, and what we could do is then multiply the probabilities up for in the sentence and try to find out whether it's likely or not. So if we have a sentence like, this is a pen, we find the probability of the word this overall, the probability of is, the probability of the probability of pen. Okay? So we get 1 per word. We probably want to care about the stop value as well, so we want to care about maybe the end of sentence as well, rather than just treat it as not the word, but I'll come back to that. So we could do that. And be aware that the probability of the sentence, if we did a unigram model, the probability of the sentence, this is a pen, okay, versus pen is the, would be exactly the same. Because it's got the same words in it. Okay, they're in a different order. And in fact, any order that they're in, the probability would be the same. Okay? But admittedly, you know, Nebuchadnezzar, 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 Nebuchadnezzar is a pretty rare sentence. Okay? Again, I've screwed it up by saying it, but let's ignore that. Okay? and that's going to have a really low probability compared to, this is a pen. Unigram probabilities sort of work. It will give you some value of what the likelihood of a sentence actually is, and it is correlated with the overall probability of the sentence. Okay. If we do this with distribution over standard English, rather than me saying the word Nebuchadnezzar all the time, the most common word almost always in any reasonable corpus of English is the. Okay. It happens about 4% of the time. So about 1 in 25 words in standard English, written English, okay, newspapers, is the. Okay? The next most frequent word, at least for this data set, was off, then and, then to, then is, then are, then in, then for. Notice all of these words are not really content words, they're what are called function words. They're some form of determiner or preposition, okay? Because they appear all over the place. Doesn't really matter if the sentence is about Nebuchadnezzar or is about Trump. The likelihood of these words is much, much higher than these other content words. If you look for this particular list and look further down, around about rank 1000, okay, what we see is the words joint, relatively, plot, del 1 sub c, which is not a common word, okay, rule 62.0, 91 and evaluated appear, although notice the probabilities are all the same, which I strongly suspect is the number of occurrences of these words in this particular data set was the same, because you've divided by the total number of words and you get the same number. So they're the same, and maybe it's 1, okay, and you could then calculate the number of words, artificially calculate the number of words. But these are much more content words, and when you've got things like del 1 sub c, which is clearly some markup for some, what do you call them, word processor, okay, well the ones at the top are going to be pretty common for almost any form. The numbers might be slightly different, but we can see what the distribution of these numbers are at the beginning. So this is a unigram distribution, so it's looking at the frequency of the word in isolation of its context. Okay. We can generate random sentences with those probabilities. Okay. So what we do is we go and get a big die, okay, 1 dice, and we can roll it, and it's got many, many sides, okay, and the sides of the sides are dependent on the frequency of each word, so it's got a probability of almost 4% to say the, and it's got a probability of some really, really, really small chance of coming out with Nebuchadnezzar. But if we have this big die and we roll it, and we roll it again, what we're going to get is random words based on their distributional property. And here, for that same set that is before, is what we get. So we get first from less this, different, 2004, out with gold, 19.2 model there, something. So we get this thing that really doesn't tell us anything, although it tells us something about what it was trained from. It's clearly something that's relatively technical. It's got CFG in it, which I suspect is context-free grammar. It's got numbers in it, so it's clearly sort of a scientific paper or something it came from. It's a little weird. But it's pretty much nonsense. You can't really get any sensible thing out of it. And remember what I said was, we're generating these words without context. Okay? Well, that's not how English works. English actually has contextualized information about how the words go. We have a left to rightness, maybe a right to leftness as well, but a left to rightness about given one word, what's the most likely thing that comes afterwards. Okay? So if I say the word president, okay, there are some words that are much more likely to come afterwards, and there are some words that are much less likely to come afterwards. Okay? So if I say the word president, what's a very likely word to come afterwards? Trump. Okay? Supposing I asked you this 10 years ago, okay, nobody would say Trump, okay? Though there's a Simpsons episode which has a President Trump in it, okay? Just as a warning that the Simpsons knows the future. So yeah, 10 years ago you would say, Obama, sorry, I have to calculate that. It's different every year when I do that example. So Obama, but you know, there are other presidents, okay? Washington is perfectly reasonable that can go in there, okay? So there are, you know, and depending on the context, it's going to be different. Can you give me a word that would be unlikely after president? Chair. President chair. Yes. I think that that is pretty unlikely. Okay. There may be some person out there who now just feels that their chances of becoming president has gone down. But we talked about them, so you know it probably has gone up. But you're right. President chair is an unlikely sequence, even though I've just repeated it a number of times in an effort to push it. But in general, outside here, President chair is going to be much less likely than President Trump. Okay? So that's sort of an important thing. The history tells you something. So if you know what the previous words are, you could try to make predictions about it. So what we could do is try and build a model that doesn't just look at the word itself with its probability. What we could do is say, depending on the previous word, we can make a different probability based on whatever that context actually is. So this is a conditional probability, so what we can do is look at the previous word, and in fact we can look at the previous word, and we can look at the previous word until we get to, say, the beginning of the sentence. So given the beginning of the sentence, what we could say is what's the most likely thing that comes after the beginning of the sentence? Will be higher than 4%, okay? And then what's the most likely thing if you're beginning the sentence? And then what's the most likely sequence to get? The chair, because chairs are favoured at the moment, etc. as we go along. Okay? So we can do that, and we can have the complete history about the probability, okay? And it's pretty good at getting the representations. And let's try and do the same thing we did with the predictions, but doing it with the full history. And so here's a generation given the full history, and we get this. Bill Clinton's unusually direct comment Wednesday on the possible role of race in the election was in keeping with the Clintons' bid for it's like, wait, that's pretty good. Well, of course it's pretty good, because we've got this conditional probability trained from data, okay, about once we've chosen the first word, the next word that we choose is going to be the most likely word that we would have given the previous one, given the data that we have. So you're pretty much going to get a sentence in your training set if you do this.
If you only have, like, say, one article as a training set, wouldn't it just basically copy?
Yes, that's exactly what it would do. And the same thing's sort of true if you have 1,000 articles. What it's going to do is you're going to roll the dice for the first couple of words, and then after that, you're just going to get indexed into one of the articles you have and have the whole sentence. You might, depending how you do your cross-sentence thing, you're going to get a full sentence. So you're never, ever, ever going to get a sentence that doesn't exist in your training set. Now, that sort of sucks, okay? Unless you've got all the sentences in the world, or much more than all the sentences in the world, all the sentences in the world and all that ever will be in the world, okay? Now, we know Google has all of those, okay? But we don't have access to them, okay? So that's not really what you want, because it would really mean that you're really doing probabilities of sentences, and that's not as interesting. There are some domains that you can get away with that, because there really is only a finite set of sentences that you could ever do. But in general, you would like to get some novel sentences that never appeared in the training set. So what we've gone from being probability of the word alone with no context to probability of given the full context. And the full context means we need all the training data in the world, or we can never predict something that's outside the training set, which doesn't seem to be the right thing that we're actually wanting to do. So instead of doing full context, we bound the context. So we only do the previous 1 or 2 or 3 or 4 words, and we build a model based on that. And we find this is pretty good, okay? It's a sort of trade-off between generalization and not having too many parameters, okay? How many words are there? Okay, so far I've got answers of chair and Nebuchadnezzar. Can somebody give another word and then another word? No, let's not do that. That's going to take too long. If you are a native English speaker, okay, which for me means you went to middle school in an English-speaking country, you probably have a vocabulary of the order. Oh no, I'm not going to give you this number. I'm going to see if I can get you to guess. Okay, so an American native speaker. I'll come to non-natives in a minute, okay, because we can estimate what that is as well. A native English speaker. How many words do you think a native English speaker knows?
About like 50,000.
50,000. So we have our first bid at 50,000. Okay, and thank you. It's sort of in the range. Okay, who thinks it's more than 50,000? I'm going to ask you for a number. A million. Okay, there's a million different words. Okay. Who thinks it's bigger than 50,000 but smaller than a million? Do you have a number?
170,000.
170,000. Okay. Standardly educated computer scientist. Okay, I'm going to say that. With a degree or doing a degree will probably have a vocabulary in English of about 25,000. Really hard to measure, okay? Because you can't ask people to write it down because they can't, okay? That's not necessarily the case that the number of different words that they would do if you asked them you asked them to generate it. It's also that they recognize. If they were an English major or they were doing something that involved more language, it probably goes up to about 35,000. Okay, so you're in the right ballpark. Million's too much, okay? Now, if you're Turkish, it's going to be, are you Turkish? It's going to be up in the hundreds of thousands because the morphology and depending how you define a word, okay? Native, non-native, so native speakers somewhere between 25 to 30,000, okay? But given one native speaker and a non-native speaker, they're not going to be the same 25,000, okay? There'll probably be a good overlap, maybe 15,000-ish, but due to interests and things, there'll be different words. Now, when you start talking about how many words in English there are, the 1 million is much, much closer to the mark, okay? So if you're going to ask Google how many words are in their language model, okay, they're not going to give you the answer. And then what you're going to do, like all good computer scientists, you're going to have a look to see the size of the int that they use to represent the number of words, and you're going to get an upper bound, okay? And it is an int, okay? But it doesn't have to be, so that means there's 2 billion. No, there's not actually 2 billion, okay? They usually take it, so to begin with, they used to do 500,000, then they did 1 million, and I think they're doing about 10 million at the moment, okay? But 10 million words in English will have many of the words in Hindi in it because they sometimes appear in English, okay? And you'll get into some relatively rare cases, okay? If you're a non-native English speaker, your vocabulary in English is probably still over 10,000, okay? And probably about 15,000, okay? If you're Indian, you're a native speaker of English, okay? It's, I'm sorry. You can't get out of that. Though you probably have a very similar vocabulary in whatever your native language is, though you might have a bigger vocabulary in English. But that's a little embarrassing, so let's not actually talk about that. What is the Hindi word for calculus? Calculus, probably. Even though there were anyway, so we've got to talk about the number of words, and let's pretend 100,000, okay, to cover lots of different people and get at least some coverage. So I'm going to be 100,000. Now we're going to talk about how much context we're actually going to care about. So if we just have one word context, so this is a one word, we know the previous word, and we're going to do conditional probability of the next, okay? And so what are the number of bigrams, word-word combinations that are possible if we have 100,000 words? 100,000 squared, okay? Which is big, okay? If you're Chinese, there's a word for it, okay? Directly. Crore. It's the Indian one, okay? It's 1 crore, which is the Indian English term for 100,000, 100,000. Is that right, or is it 1,000? Is it 1,000 times 100,000? It's 100,000. Oh, I've never survived in India with. Anyway, 100,000 times 100,000 is pretty big, okay? But that's okay. We've got computers. We can actually do that, okay? So what we can do is we can calculate for every word what's the probability of it being followed by every other word and itself, okay? Because we know that Nebuchadnezzar can appear as a bigram. Okay? If we do that and build a generation model, we get something like this, okay? Some bunch of nonsense, Model S are also being completely surpassed in performance on drafts on online algorithms, can achieve far more, yeah, maybe, okay? There's some relationship, but because you're effectively each time forgetting the previous word, it's a little bit random. But bigrams are sort of okay. We could go to trigrams, and the number of trigrams with 100,000 words is 100,000 times 100,000 times 100,000, which is big, okay? However, many of these 3-word sequences have never existed, okay? Prove me wrong, say them all. You're not going to be able to say. You can write a program to generate them, but many of them have never actually appeared in continuous form. I'm going to tell you a little story about that. I work in speech, so I actually don't just care about words, I care about the smaller units that are called phonemes. The phonemes are the sounds that when put together form words, okay? In American English, there's about 45 phonemes. And so when you're trying to get language models in the phoneme space, it's much smaller than what you do for words. So you can get bigrams by having 45 times 45, and you get trigrams of 45 times 45 times 45, which is about 70,000, which is still practical to actually try to get things, okay? However, some of these phoneme sequences really are incredibly rare, okay? Because you can't say them, okay? So there's this other thing, I mean, you just physically can't do them. So if one of the phonemes in English is, okay, which appears at the beginning of hello, okay? Now, you can't ever really get after itself, because you can't have hello, okay? And never appears at the end of a word, because then you can put 2 words together to be able to do it. So that one doesn't actually appear, okay? But there's some that are there, but they're just very rare. Oi is one of the rarest phonemes in English, okay? Je is the other one that's pretty rare. And you think about, so does oi ever appear naturally, okay, in English? Are there any examples where you have it? The trick is you look for word boundaries. I don't think it would ever appear. So you have a word that's ending in oi and starting with oi. And I was looking for some actual real example of this. I thought, I'll search Wall Street Journal and see if I can find some examples. So I converted Wall Street Journal into phonemes, because I have tools to do that, and looked to see whether there's any examples of oi, and there's none. At least for the 6 years that I did it from the mid-90s. I thought, oh, there's none. Okay. So I then searched my email and thought, maybe there's an example of that. And I found an example. Actually, I found 6 examples in my email, but when I looked at them closely, they were all the same example, because they were quoted things in an email message I had with a friend of mine. And the example was, I'd been desperately looking for examples of oi in natural speech, but couldn't find any. And so I made one up, toy oyster. Okay? So toy oyster, which I think is relatively uncommon, is an example of oi. Soy oil is a natural example that I've since discovered. But back to the words, Okay, bigrams, yeah, this is better than the unigrams, but we have 100,000 times 100,000 numbers that we have to actually get. And some of them won't exist in our training data. Okay. If we go to trigrams, okay, so it's 100,000 times 100,000 times 100,000 numbers you're going to have to do, and that's still possible unless you do something, you have to do some collapsing because it's probably going to be too big. This is what we get when we get to generate, so we still get somewhat nonsense at the beginning, but then we get these equations were presented in both cases as scores something into a probability distribution is even smaller, r equals 0.05. This is exactly something during DA and gradually relaxed. Okay, I have read more understandable scientific papers than that. Okay, that's not a good sign, but it's beginning to capture something. As we increase the context, we need more examples to be able to estimate these forms. Okay, you can guarantee if you're going to do trigrams, so you need to look at all possible combinations, that even for 100,000 words, you're going to not have examples for some of those in your data. Pretty much guaranteed. Because the distribution of these, okay, are not going to be uniform. Okay, they're going to have some distributional property, and something like off the will be incredibly common. Okay, while Nebuchadnezzar is going to be incredibly rare. Okay, unless it's my lecture notes, then it's going to be. I'm sure you can come up with something. So we can increase context and get better. And Google a number of years ago released a 5-gram language model for all the data that they could reasonably train on at Google. 5 grams. Okay, and the vocabulary I think was about 1 million. So it's 1 million times 1 million times 1 million times 1 million times 1 million. 5 grams that exist there. And we tried to use it for various things. We think, oh, this is cool, I'll download it. No, you won't download it. Okay, it's really big. It's many, many terabytes. Okay, okay, so that's not reasonable, but you can try to get subsets of it. And of course, it's completely out of date. Okay, because it doesn't have Brexit in it, because it was done in 2005 or something. Okay, back in these days when Britain was part of Europe and it isn't anymore. At least it won't be by the weekend. So we have this problem of number of words and getting context, but the more context we do, the more data we need to be able to train it. And realistically, you know, if we're talking of all of Wikipedia is not enough, it's sort of hard. So we could do all of Wikipedia and all of the news service, but that's, you know, maybe only 10 times bigger than Wikipedia. But you need to be thousands of times bigger than Wikipedia, or you need to be hundreds of thousands of times bigger than Wikipedia, okay? And much as you think there's lots of data out there, there isn't really after a while, okay? But, go back to this issue of the definition of what a word is, okay? In English, we think a word is something that's got spaces, white space at either side, or is at the beginning or the end of the sentence. Yep, that's a first approximation, although we have non-trivial issues with words like Los Angeles, okay? It has a space in the middle, or it's 2 words. But actually, it's sort of conditioned with itself, because the pronunciation of the S in Los is actually pronounced as a Z, and not as a S, as it is in Los Altos. So actually, there's a conditional probability about how the pronunciation is. So it really is a single word, even though it's got a space in it. Then we have things like punctuation, which normally gets written without spaces round about it, but it would be a good idea to model the punctuation as well. Now, this is something that we've talked about before. Most of the work that we do in NLP, we end up tokenizing the string of characters into what we consider to be words, okay? And for the most part, that means punctuation gets separated off, because it tells you something, okay? And additionally, we care about the beginning of the sentence, okay? So we have to have a new symbol that doesn't exist elsewhere
it's the beginning of the sentence, so it's a start. And when you want another symbol for the end, that means the end of the sentence. Because we want to know what's the probability that the next word is end of sentence. And that has to be some word that doesn't exist elsewhere in our vocabulary. It's pretty easy to come up with one. Do we care about upper and lower case? It'd be nice if we didn't need to. Or do we care about mixed case? Do we care about all uppercase versus all lowercase? There are a number of examples in English where we get a different word depending on the casing. Okay. There's a place in the south of France, a city called Nice, spelled N-I-C-E, which of course is pronounced nice. Okay. But if it's got an uppercase N, it is more likely to be the French city than it is to be the English word nice. Not always, because nice can appear at the beginning of the sentence and be capitalized, or maybe it's in a headline or something. But, you know, there's some distributional property that's different. Okay? So, maybe we care about case. Actually, for the most part, when we're doing work in NLP, we do not care about case. Everything gets flattened. Okay? And that's probably right, except when it's very occasionally wrong. Because not everybody uses casing consistently. Not everybody capitalizes at the beginning of a sentence. Though newspapers almost always do that, but email and Twitter maybe doesn't. So we probably flatten case. Okay? In other languages, that might not be the right thing to do. In German, for example, where all common nouns, all nouns, have got are capitalized. Maybe you might want to do that for German, but that's a choice. Okay. What's actually a word? That's the next thing that's hard. It's sort of fine when it's written. What do we do about spelling errors? Well, they're common, and they can be stupidly put extra spaces in, or letters can float from one word to the next because people are typing too fast. Autocorrect doesn't do that properly. What about speech? Because people don't speak fluently all the time. They make errors when they speak, and humans are pretty good at ignoring the errors in speech, especially localized errors. They just don't hear them. They're gone. Okay? So if I say I do mainly business processing, most people hear I do mainly business processing, and they don't hear the fillers, and eh. They don't hear the partial words and repetitions, because people do it so often that you just try and go. If they do it too much, you notice it, okay? And occasionally you notice that there are speakers who are out there who never do it, okay? You should be aware that they are evil robots who are trying to take over the world. Bill Clinton, okay? Not Hillary Clinton. Bill Clinton is really good at speaking continuously without making speech errors, which is deeply frightening and deeply impressive. A number of people who speak professionally have learned to do that. I have not, even though I do speak professionally, so I make errors all the time. But we have to make a choice about that. We have to make a choice of which of these are words, and try to decide whether are the same or different words is incredibly hard. Okay, maybe people use them in different ways depending when they're stalling and thinking about what comes next, or maybe they don't, and you just collapse them into the same one. I don't know. Yes. So these n-grams are pretty good at modeling. They will do something about modeling, and they're actually practical enough to use. Okay. The 5-gram stuff is just too big. It's not reasonable to use in any form. Yes, it's all online that you can get from Google, and I think they updated it as well. Do these models of English know English? Do you think they know English? You understand English? No, they don't. They're just some bunch of numbers that you get out of models. They will score a sentence and tell you whether this sentence is more likely than another. And that's very useful, and there's lots of things we do in speech recognition, machine translation, where we actually really need to do that. For example, if you're trying to generate questions for, say, some project in some NLP class, really fascinating NLP class that you're doing at CMU, and you're trying to generate them by a bunch of rules, it might be quite nice to know which of the questions you generate are better or not. So if you had a language model for questions, you might be able to do that. So if you had all the questions in the world and built an n-gram model, it might be quite good at telling you which of your questions are better. There are always unknown words, okay? And so I talked about if you train on everything and use full context, you're only ever going to get things from the data from the training set. But let's talk about the words. We said there might be a million words, but there's always one more word, okay? It's not just one word. There's always words that your system don't know. There's always words that you don't know, okay? And there's some circumstances you're much more likely to find words that you don't know. So for example, a student here who you don't know at CMU comes up to you and says, my name is, okay? The word that comes afterwards could easily be a word you've never heard before, okay? It might not be because you're familiar with most of the common names for most of the countries around the world, but still, it could easily be a name that you've never heard before, okay? Likewise, okay, if you're in a class and you're talking about some technical thing in biology and the professor says, and this is called, the word that comes next, it might be a word you've never heard before, okay? Likewise, you get somebody who says, I've just started this wonderful startup in California, it's the Uber for Uber, I don't know, the Uber for something, okay? Our company name is pretty much guaranteed to be a name that you've never heard before that's misspelled of another word, okay? But actually, there are other words. It's not just these extreme ends. There are other words that are just unknown. And it could be that the data set that you have just never had that word in it, okay? Nebuchadnezzar never appeared in the Wall Street Journal for 5 years in the mid-90s, okay? Poor guy, okay? He's fairly famous, okay? But he never appeared, okay? And yet, I use that as an example of a word that, you know, is low frequency, but not really low frequency, okay? I could pick some Scottish dialect words that nobody would know, but I'm not going to do that. But unknown words are a thing that require you to model, okay? But you can talk about them even though you don't know what they are, okay? So I said you're likely, or more likely to hear an unknown word if you're in the context of my name is, next word. It's got a higher probability of being an unknown word, okay, than if I said, here's this book that I'm reading to my 3-year-old kid, and it says, look in the farmyard, the animal is, okay, and you probably can guess one of about 10 animals that it's going to be, okay? And it's unlikely to be an unknown word, unless it's an interesting book for a kid. So we're going to have to model unknown words, okay? So I'll come back to that in a minute. N-gram models, okay, can be fully represented in finite state machines. They're actually equivalent, okay, and not everybody knows that. And you can do lots of things in finite state machines that are a little bit harder than simple N-gram models. You can do simplification. You can actually do other things about reducing their size in interesting ways and getting approximate. And you can also do very efficient representations of them. And so it's worth knowing that there is this very simple mapping between unigram, unigram single state, bigram is effectively a state for every previous word, trigram is effectively a state for every 2-word context, okay, and so you've basically got a state for every context. Starting and stopping I mentioned, you are going to have to care about the beginning and the end. Okay, you're going to have special symbols for those, okay? And if you're using anything more than bigrams, you're going to have multiple special beginning symbols, and people usually just repeat them. So effectively the beginning symbol here is written as an arrow, okay? You can assume there's an infinite number of those that appear before the beginning of the sentence. So if you're going to do a 10-gram model, you know, it's okay, there's 10 start symbols before there. And so when you're beginning the sentence, your context is 10 start symbols. And what's the likelihood of that? Likewise, at the end, you want to have a probability of stopping. That's not a period full stop at the end, okay? It's an actual end of sentence, because it's not always the case that we have punctuation at the end of sentences. Okay? There's a probability it might end without that. And we've got to have a special symbol for the end of sentence. And so when we're looking at the context, what's the likelihood? The next thing is Nebuchadnezzar, chair, or stop symbol, or everything else. Evaluation. So I can build all these models and I can say, oh look, that one's better, but that's not what we do. What we really would like to do is we'd like to know, given how we've trained a model, we'd like to measure with a number how good it is. Okay? Because we're going to build lots of different things and we're going to find out which one's better. Okay? Is it better to get more data? Okay? Is it better to reduce the vocabulary? Yeah, I'm going to lose the outer vocabulary ones, but I might better estimate the other part of the distribution. The way we typically do this is we have a model and we run that model on a test set. That test set should not be in the training set. So what we do is we get all of the Wall Street Journal, if that's what we're doing, and we maybe take 1 day every week and hold it out as test, and we build a model and everything else, and build the model on 6 days a week, and then find out how well it predicts that remaining thing. You have to be careful about when you're building a training and test set, because if we did that and accidentally pulled out the Sunday edition of the newspaper every time, Sunday edition is typically different than the rest of them, so it has a different word distribution, so you probably shouldn't do that. So maybe if you took every 10th, it would then page through the week and it'd be a little bit better. It doesn't matter if you have enough data and there's some overlap. Okay, that's okay. But they should try to be separate. Okay. We have a measure that tells us how well, given a model and a test set, how well that test set matches that model. It's called perplexity. Okay, and it's fundamentally to do with entropy. But it's slightly manipulated to give us a more interesting number. But it's really to do with entropy. It's basically how predictable is the test set. That's what you're really trying to find out. So how good does my model effectively model this set of sentences that I've never seen before? Okay, that we hope is in the making. The perplexity is the probability of the test set normalized for the number of words. So that's what it actually is. It really is based on entropy, okay? I can never remember these formula. I have to go and look them up when I need to put them on the slide, okay? Which you should do too, okay? But you should remember that perplexity is the measure for finding out whether a language model is good or not. Gives you a number. And there's the bigger that number, the bigger perplexity, in some sense, the worse your model is, or the harder the task is. Okay, so there's some uses of English that are much, much harder, okay, than other uses of English. So data set. So we think about newspapers. Okay, so the Wall Street Journal, the data, a unigram model is a perplexity of 962, the bigram is 170, the trigram is 109. So as we get a better language model, the perplexity goes down because we've got a better model. Okay, but that's about the magnitude that we're talking about for newspapers. Different tasks have very different complexities. So Wall Street Journal, the trigram is about 109. The bus information query system that we used to run here, telling in the time in the next bus before we all had smartphones, it has a perplexity of about 25. It's an easier task. In fact, the only thing that's really hard about it is the bus stop names in Pittsburgh. There are 15,000 bus stop names in Pittsburgh. Okay, just thought I'd tell you that. It's actually something like, depending how you really count, 1,400 and something. The most interesting Pittsburgh bus stop name is unnamed stop number 2. What? There's no unnamed stop number 1. Or if there is, some poor bastard's standing there waiting for a bus and it won't come. But, so higher, So perplexity is really based on conditional probability. Okay, so the higher the conditional probability, the lower the perplexity. The higher the conditional probability means that if I have context, I really can predict what comes next. Okay, that's really what it means. And this thing's a little weird, this next bit, but it's really useful. Perplexity is sort of the average branching rate. So the number of next words that could follow given any word. And that's a really useful way to think about it. Okay? So if you say Wall Street Journal is 109, that means on average, given any context, there's about 109 different words that could come afterwards. Okay? And that's sort of just a good way to model it. And most people think about it like that. Okay? Likewise, so it means if you get a new model and you go, yeah, I've got it down from 109 to 108.3, okay, it doesn't matter, okay? But if you go from 109 and bring it down to 27, that's really good, although I'd be suspicious that something's gone wrong, because that's a very big improvement. That would be sort of hard. Okay? So perplexity to measure model. So let's go back to the unknown words, the unseen words. What's the probability of this word you've never seen before? Technically, the correct answer to that is 0. I've never seen it before. It was never in my training data. It's not in my vocabulary. It's not a word. Okay? Now, that sort of works. And that means if you've got a speech recognition system, it's going to recognize all the words you know. And when somebody comes along and says Nebuchadnezzar, the speech recognizer is going to fit Nebuchadnezzar to some words it knows. Now, I do that when somebody says to me, my name is Nebuchadnezzar, and I say, oh, you're called Neb. Okay, and I misrecognize, I don't do that, but you misrecognize with the base words that you actually know. Okay, now, that sometimes works, and you might discover for years that you think somebody's name is something and it's not. But it is extremely likely that your test set will contain words that your training set has never seen before. To the extent that if it doesn't, there's something wrong. Okay, it's not a good test set. Because word distribution for novel words is sort of guaranteed. 4% of the tokens every day in the Wall Street Journal have never appeared in the Wall Street Journal before. 4%. It's quite a lot. Okay? Now that doesn't mean that this new word's going to come into being and we're going to talk about it forever. Most of these words come in, they appear a few times and then disappear. There are often some town or village where something happened and they're in the news, and then we forget about them afterwards. I mean, the people in the village don't forget about them, but the rest of us do, okay? Or a person's name, something like that. But sometimes it might be a company name, okay? Google didn't exist in the way that it was written before Google existed. So if you go and look at the Wall Street Journal, which all this data that we do in the mid-90s, Google doesn't appear. Neither does Facebook, okay? Apple appears, so does Microsoft. Baidu doesn't, for obvious reasons. So how do we model an unknown word? And the answer is, you should model the unknown word. You should say there is an unknown word, and I could say something like, X% of my words that have got very low frequency, I'm going to treat them as unknown words. And I'm going to label them not as their original word, I'm going to replace them with the unknown word symbol, and then I'm going to build my model. And then when I'm doing my test set and I'm finding out a word, I look up my vocabulary. If it's not in my vocabulary, I don't map it to, well, I map it to the unknown word. It becomes the unknown word. And the unknown word holds together all of the unknown words or all of the low frequency words, and you now can have a probability function that tries to predict what's the likelihood that I have an unknown word coming up next. Okay? You don't know what it is, but you know there could be an unknown word that's next. And that works pretty well. Okay? You could consider multiple types of unknown words, and people do this. Do we have an unknown word that's capitalized and an unknown word that's not capitalized? And that might be good for getting names and not names. And so people do things like that, so they might have some distributional thing. Okay? But modeling the unknown word is a good idea by having a symbol that means unknown word and estimating its probabilities by taking some number of low frequency words in your data set and just pretending in your training set that they're unknown so you can get estimates for your unknown word. When you're building these n-gram models, in fact when you're building any model at all, you're going to have partial data for estimating the probabilities. You're not going to have all of the data, okay? So if you're doing trigrams and you have all of Wikipedia and all of the news that's been published in the last 20 years and all of Twitter and all of Facebook, there's still going to be 3-word sequences that have never appeared before that will appear tomorrow, okay? And if you look at the probability distribution of whether it's very likely that there'll be unknown ones that will appear. You don't know which one the unknown ones are, but there will be some that you've never seen before. Therefore, when you build your nice fancy trigram model, it's a good idea to try to estimate, okay, what the probability would be for something you've never seen before. Okay? Now we know it's low if you've never seen it before, but you'd like to have something better than the smallest possible number. Okay? We'd like some number to be there, and we'd like to take into account what we're looking at, context if we have it, or maybe look at some other pairs to try to find out what it might be. The simplest way to do this, okay, is what you do is you look at all of your possible words and all of your possible n-grams, and what you do for all of your 0 cases, you just add 1. What? You just assume that everything appears once, and everything else is more than 1. Okay? It's often called add-1 smoothing, but it's also called Laplacian. It sounds better when it's called Laplacian. Okay? Just add 1 to everything. Okay? So what you're really saying is your least frequent thing always appears, and everything that actually appears once has got 2 or more. Okay? And it sort of works. Okay? If you have enough data, it actually works quite well. Maybe you don't want to add 1, maybe you want to add a half. Wait, we're talking about counts of the number of words. Can you really have a half? This word appeared at half a time, okay? And the answer is, yeah, it's not a problem at all, okay? As long as you didn't declare it as net when you were calculating the numbers, you can quite happily make that float. In fact, maybe it isn't 0.5, it's something else. And I'll talk about some various ways of trying to represent that number, about that small number that you would like to add. You still need to know all your vocabulary, so you still need to care about the probability of the unknown word. That's not going to solve the unknown word, but it will allow you to get estimates for the unknown context that you're actually in. One of the standard ways of doing smoothing, as it's called, this adding 1 or some other techniques, is called good Turing smoothing. For years I thought that good Turing smoothing was an algorithm done by Alan Turing that was good, and there's some other paper about the bad one. Okay, and it's not the case at all. Okay, Good was actually a professor at Virginia Tech. He's a Brit, or was a Brit, who died relatively recently. He died in 2009. His name was I.J. Good, and he went through his academic career working with various algorithm developers because they could get a much cooler name for their algorithm if they worked with him, because they could put good at the beginning of their algorithm. Okay? While the poor guy, Mr. Charles Badd, has never had any co-authors for any of his algorithms. It's a way cool name. I wish I had the name Good, because my name doesn't work, because it's also not a name that you might want to have at the beginning of an algorithm. It doesn't give the impression of being good. Anyway, Jack, I think his name was, Jack Good worked with Alan Turing, the Alan Turing, who effectively invented computing by some definition of computing, They worked together at Bletchley Park doing cryptography, but this stuff was done later than that, post-Second World War, and they were looking at exactly this issue of how can you build language models and what's the most optimal way to do the smoothing, should you add one, and what they actually discovered, instead of actually adding one, okay, what you can do is better than that. What you can do is you can look at the distribution in your data, okay, of everything that currently, before you do smoothing, currently appears once, everything that currently appears twice. So there'll be a whole bunch of things appear once, a smaller amount of things that appear twice, an even smaller number of things that appear 3 times, and even small. And so you'll get this distribution, and then there'll be a few things that appear 17 million times, okay? For example. And so what you get is you get this curve. You get this curve of the distribution of occurrences. And what you can do is you can extend that to get a number that's based on estimated, what's the number that I should get, the number of things that's going to appear 0 times. And you can sort of get an estimate from that, and from there you can estimate a probability. It's pretty easy. Actually, the other thing I know about Jack Good is that he gets a credit in the movie 2001: Space Odyssey as a technical consultant about high-end computing. Alan Turing didn't get that, but Alan Turing is no longer alive. There's another technique that we can use if we're trying to look at trigrams, and in fact this is often the case. If you're trying to get the trigram probability and you don't have one, what you do is you go and find the bigram probability, because it's a good estimate, okay? And if you don't have the bigram probability, you have to go back down to the unigram. And so you can get away with doing smoothing only on the unigrams, which makes life a little bit easier because there's less. Okay? And so we do that. Yes? So what we've talked about today is language models, and we've talked about language models in a very explicit way of saying, can we get the word probabilities by calculating it from data, by looking at the word probabilities, and everything does that, including all the neural stuff, okay? They do interesting smoothing thing in the neural stuff, but they're still looking at the distribution of words that are in the corpus. So you actually have to have all of the words and all of the context and be appropriate in order to be able to build that. So what you have to do is you have to count the word occurrences, okay? And then you normalize by the number of words to be able to get probabilities. Okay? To deal with missing things, you can do the add 1 or add epsilon or add something, or good Turing, which is adding something but estimating what that something actually is. If you don't have a trigram, you go down to bigram, you go to bigram, you go to unigram. Or you could actually do it, because you might have 7 grams for some things, and so you get 7 grams, which would be really good, and then go down all the time. There's a number of other little tricks that make subtle differences and can be better, okay? And I'm going to talk briefly, just going to mention these other ones. There's another thing called cat's back off, you can look it up. But the second one is called stupid back off, okay? And this was done by Google, Jeff Dean at Google. And it's called stupid because it is stupid, but it's an actual thing, okay? And there wasn't somebody called Mr. Stupid, okay? Also would not be a good name for your algorithm. But anyway, I don't know, I mean, we have stupid back off. And it's not clear from the paper, I haven't actually asked Jeff Dean, I've met him a couple of times, whether it was a bug in their code or whether it was something they actually explicitly tried. But notice what I say is you count and normalize. So what you can do is you can count the number of occurrences of things and then you divide by the number of words so you get a probability. If you don't divide by the number of words and just use the count, it still sort of works. And it still sort of works because bigger is still bigger, okay? And smaller is still smaller. And they did this, they claim in the paper, they did this because it saved the passive normalization. And if you're going to normalize over 100 million words, it takes an awful long time. But if you're just going to count things, you can actually do things in parallel explicitly in the paper, because it was Jeff Freeman doing this about map reduce. You actually can get rid of the reduce step and just do the map step and do everything, the counting in parallel. And that's sort of cool, okay? And it sort of works, but it only sort of works if you have a lot of data. That's what the Google paper says. Google says it only works if you have a lot of data, okay? So you will never have a lot of data compared to what Google, unless you're working at Google, okay? And then it'll just be fine. There's also another thing called Kneser. Nye's a professor at Aachen in Germany, and Kneser is at Amazon, I think. At least the last time I spoke with him. And there's other techniques of looking at, again, the distribution of them and trying to do estimates. These things make a big difference when you have a ridiculously small amount of data or a really, really, really large amount of data. And in between, who knows, okay? You can get the perplexity values out when you do these different techniques, but it maybe doesn't make much difference. Perplexity is a measure of your language model, gives you a number, but it doesn't mean that your actual task gets better. And you should always Okay, that's it for today. So you've learned about language models in the simplest possible way. Oh yes, I was going to briefly mention about some of the new language models, the Euro language models. Not actually going to go into details about them, but they still sort of do the same thing. They're looking at lots of data. They're typically better at dealing with context. So BERT, which is one that we'll talk about in more detail, looks at the future, which you can't always do. While GPT-2, which is from the Allen Institute, does not look at the future, but it's trained on a Google amount of data, and it is very, 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 very good. But you still measure everything in terms of perplexity, and you still have to train it on data. And if you're expecting to take GPT-2 and get it to estimate things for Twitter, it's not going to work, because Twitter's a different language, and Twitter wasn't in the training data. So you really have to have a match between the same data. Otherwise, the scores that you get out of your language model won't be meaningful, mostly. Okay, that's it. Is there any questions? Okay, thank you.